Hi everybody, so we're going to go over the proofs of the properties of logarithms. And a lot of these proofs are going to depend upon us being able to move back and forth between exponential form and logarithmic form. And so just a quick reminder, the exponential form of an equation would be b raised to the m is equal to x, and then that exact same expression written in logarithmic form is the log base b of x is equal to m. So the log base b of x is equal to the exponent that you would get in exponential form. Just keep in mind these two equations are the exact same equation. They are just written in different forms. So now we're going to go through the proofs of these properties. The first proof that we're going to look at, or the first property that we're going to look at, is the one about a product. So the log of a product is the sum of the logs. So log base b of x times y is equal to the log base b of x plus the log base b of y. And the way that we go about the proof is that we're going to let the log base b of x be equal to m and the log base b of y be equal to n. And then that's me writing it in logarithmic form, and then I'll rewrite both of those things in exponential form. So again, log base b of x is equal to m means that b to the m power is equal to x, and that's what you see right here. And then similarly, b to the n power is equal to y, and that's what we see right here. So we're going to start by looking at the product x times y. And since x and y are both equal to b to the m and b to the n respectively, I can write it as b to the m times b to the n. And then this is a product, and I learned in my algebra class that I can add those two exponents together. So I can write it as b to the m plus n. So I have x times y is equal to b raised to the m plus n. And I can think about that as being in exponential form. And so I'm going to write it in logarithmic form, which would be the log base b of x times y is equal to m plus n. So all I did was rewrite this as in logarithmic form. And then if I resubstitute for the values of m and n, m is equal to the log base b of x, n is equal to the log base b of y, I see that I get that property. So now the log base b of x times y is equal to the log base b of x plus the log base b of y. That's supposed to be a y right there. Sorry. So therefore, log base b of x times y is equal to the log base b of x plus the log base b of y. So that's the proof of the first property. And that may seem a little rough the first time that we go through it, but what you're going to see is that this idea is going to be what gets us the rest of these properties. So the second property of logarithm says that the log base b of x divided by y is equal to the log base b of x minus the log base b of y, so that the log of a quotient is the difference of the logarithms. And I'm going to start this proof the exact same way. I'm going to let m be the log base b of x and n be the log base b of y, which implies that b to the m is equal to x and b to the n is equal to y. That is the exact same thing that I wrote at the beginning of the previous proof. And the next step in the previous proof was that I started with x times y. Now I'm going to start with x divided by y. And so I can substitute in those values of b. So x divided by y is going to be b to the m divided by b to the n. My algebra teacher taught me that if I am dividing two things that have the same base, then I subtract the exponents. So that's b to the m minus n, which I can rewrite as x times y is equal to b to the m minus n. And now this is in exponential form. I can write it in logarithmic form as the log base b of x divided by y is equal to m minus n. And then I will substitute in the two things that I started with m and n. So I get that property. There's that. I must have copied and pasted that typo. So we're probably going to see that typo the rest of this video. So log base b of x divided by y is equal to the log base b of x minus the log base b of y. So there's the proofs of the first two properties. Next, we look at the proof of the third property. The log base b of x to the r is equal to r times the log base b of x. This is probably the most important property, the one that gets used the most, that says that if you've got a log of something raised to a power, you can take that power and move it in front of the logarithm. We're going to see a very similar proof to the previous two, slightly different. This time I only need one logarithm, so I'm going to let m be the log base b of x. Rewrite that in exponential form. B to the m is equal to x. And then I will start with that equation in exponential form, and I'm going to raise both sides of that equation to the r power, which is something that I'm totally allowed to do. On the left side here, I have an exponent. I have a base raised to a power, raised to a power. My algebra teacher taught me that I would multiply those two powers together. So I could multiply them as to get b to the rm is equal to x to the r. And then I'm going to rewrite that in logarithmic form. So the log base b of x to the r is equal to r times m. Then if I resubstitute in the value that I had for m over here, I would get that the log base b of x to the r is equal to r times the log base b of x. So that's the proof of the third property. Therefore, the log base b of x to the r is equal to r times the log base b of x. The fourth property says that if you've got a base and you have an exponent that is a logarithm of the same base, then it's almost like all of this just cancels out and you end up with that argument of the logarithm. The way to prove this, this one is actually probably the easiest of them, but it's so easy that it can be a little bit confusing. I'm going to consider log base b is equal to the log base b of x is equal to the log base b of x. I just wrote the exact same thing on both sides of the equation. And if I think about this as being an equation in logarithmic form, that is that a log base b of x is equal to something, and it turns out that something is a logarithm, but if I just ignore that it's equal to something, and I rewrite that in exponential form, it will be b raised to that log base b of x power is going to be equal to x. And so rewriting that in exponential form makes it be the thing that I ended up having to prove, right? So that one, like I said, that one's pretty straightforward, and that makes it a little bit confusing. All I'm saying is the log base b of x is equal to the log base b of x, and then rewriting it in exponential form. Last thing that we're going to look at is the change of base formula, also a really important one. This is the thing that, most calculators just have a log base 10 and a natural log, a log base e, and this is what allows us to get any type of a logarithm into one of those two log bases so that our calculators will work. It says the log base b of x is equal to the log base c of x divided by the log base c. That should be a b. Wow, I got lots of typos here. So that should be a letter b there. So I'm going to start by letting m equal the log base b of x. And then, similar to what we had been doing before, that says b to the m is equal to x. And then I'm going to take the log base c of both sides of this equation. So I get the log base c of b to the m is equal to the log base c of x. In one of the previous proofs, we proved that if you've got a log of something raised to a power, we can move the power in front of the logarithm. And so if I do that, I get m times the log base c of b is equal to the log base c of x. I'm going to divide both sides by this logarithm to get m is equal to the log base c of x divided by the log base c of b. And then what was m? It was the log base b of x. So I get the log base b of x is equal to the log base c of x divided by the log base c of b. Again, that should have been a b right there. So those are the proofs of these very important properties of logarithms that we're going to use a whole lot. And what these proofs do is justify our ability to be able to use them whenever we need them.